Okay. All right, so basically we're going to finish off integration. We've basically got one integral to go. And we saw that we could do things with path integrals, or sometimes called line integrals. The last thing we're going to do is how we calculate surface areas, which leads to an extension of something called surface integrals, which we used to do in this unit, but we don't anymore because we need to cover a concept called vector fields, which we don't have time for anymore. That topic's been dropped. So we're just going to do a surface integrals. Oh, sorry, I'm sorry, before I get started. Now, there was a typo on this slide with that was a full stop instead of a comma. Right, so I fixed that. That's not a big deal. But I also realised for some reason the last slide was missing. I don't know what the hell happened to it. But so I've re-uploaded these lecture notes. So if you printed these out before the lecture yesterday, this last slide won't be there, which we'll talk about in the third lecture. So just if you're printing them out, just make sure you reprint them out. Right, so to do surface integrals in general, and what we're going to do, surface areas in particular, we need of how we parameterise the surface. So when we were looking at vector functions, we used it to parameterise lines in 2D, 3D, or in fact any dimension. So to parameterise a surface, what we do is sitting in a two-dimensional surface, we need two coordinates. Normally we use u and v. Right, so the aim here is to come up with a suitable parameterisation that fits the problem. Then you need the two tangent vectors, which are just the partial derivatives with respect to your two variables, and from that you construct the normal vector. Very similar to what we did when we found the equation of a tangent plane. We found it easier not to work with two vectors that lie in the plane, but work with one vector that's always perpendicular to the plane. Same deal here. It'll turn out it's easier to work with a normal vector always perpendicular to the surface, which we can always construct via the cross product. Now, unlike with lines and planes, the way we'll do these parameterizations, either the spherical coordinates, cylindrical coordinates, or brute force, we won't do any others. Right? If it's more complicated than that, I will tell you the parameterization. Right? I am going to do an example that's in the practical class next week that extends this simple idea here. Okay, so when you want a straight line, so when we're talking about parameterizing a line, the easiest way to parameterize a straight line is to do this trick, where it's the start point plus the difference between the end point minus the start point times t. Because then t equals 0, you're at the beginning, t equals 1, you're at the end. It's the easiest parameterization to work with. Right? I'm going to do an example like that with a surface, but going through the parameterization of a surface, we can now calculate the area of any surface that sits above any region in the xy plane. Just like the line integral gives us the area of a curtain drawn above a line in the... So just like the line path integral gives us the area of this curtain, imagine you have a surface and you lift it up, and where that surface intersects some other surface, so where that region in the xy plane intersects some, you can find that surface, so you can find the surface area of any surface. And in fact, this is the formal mathematical definition of surface area, is actually formally defined as this double integral, which we're going to do in a sec. Right, so say we've got a suitable parameterization that we've come up with, either cylindrical coordinates, spherical coordinates, or we brute force it, or I give it to you. From that we can find the partial derivatives with respect to our new coordinates u and v. I can find the normal vector by finding the cross product, right? And then what I can do with it. So this is basically the problem. Imagine I've got some region, now it's a circle just for the hell of it. It doesn't have to be a circle as long as it's closed. The question we're asking now is, remember the standard double integral would give me the volume bound by the surface that sits directly above that region D in the xy plane. What I'm asking for now is what is the area of the surface that sits directly above this thing, right? So imagine it's like a, for argument's sake, imagine it's a cylinder intersects it. What's the area of the top where the cylinder bit slices through the surface? What's the area, right? So I can find the surface area. If I wanted the surface area of the whole surface, I'd just do this integral over everything, right? It turns out that this is the formula to calculate it. Now, this is proved in the unit reader using Riemann sums, if you're interested. It's quite laborious and tedious, but it's in there, right? But essentially, it is the second part, right? It's basically this formula. It's the length of the normal vector, right, which we find by the cross product, integrated with respect to du dv, or as we know, the order doesn't matter, du dv or dv du, right? So where the region is now described in your new coordinates. So if you brute force it, that's just dx dy, right? If you use spherical where rho is constant and theta and phi, that'd be d theta d phi or d phi d theta, depends on the question, right? Notice the similarity. First thing to note is notice the similarity, if you squint, between this formula for a surface area and this one for the length. Right? They're kind of similar, aren't they? One's a single integral over the length of a certain vector, so a single integral of the length of a certain vector, and this is a double integral of the length of a certain vector. Right? Kind of similar. You know? So I can find, this means I can find the area, and in fact, as I said, this is actually the formal mathematical definition of area. This is how we calculate. So we use integrals and areas to calculate volumes, lengths, and areas. We can do them all with integrals, all of them. Right? Integrals, very powerful thing. Right. So let's go through a special case. Let's say we've got one that we brute force. Right, so what I mean by brute force, we've got some surface z equals some function of x and y. I'm going to brute force it. Just let x equal u and y equal v. You know, it doesn't lend itself to spherical or cylindrical coordinates. It might lend itself to some other coordinate system. As you might remember that book I showed you with the diagrams of the cylindrical and spherical coordinates. There's lots and lots of 3D coordinate systems which you might come across as you go on. We're just going to do the two of them. But let's say we've got one and we're just going to brute force it. Right? What I'm going to do is work out what does this formula look like if I just brute force it. Well, in this case, if I just brute force it, my suitable parameterization is a 3D vector u, v, function of u and v, x, y, z, basically. You know? Now, I need the tangent vector, so partial derivative of my parameterized vector in terms of u is 1, 0, partial df du. With respect to v, 0, 1, partial df dv, so it's the you know, remember the trick on how we do this, right? We find that we construct the 3 by 3 matrix, work out its determinant. Remember, that's a shortcut trick to calculate the cross product. You do it or you get that. That looks familiar, doesn't it? That's the formula we derived when we were doing tangent planes. Right? A normal vector was minus partial df dx minus partial df dy and 1 if it was explicit. Right? Same thing, it's just u and v instead of x and y. Find its length, and that's my formula for an explicit function. You look at that and think, oh, that looks kind of familiar. Well, remember, if we wanted the length of a curve, and we had it explicitly as y equals f of x, or f of t, makes no difference, it's a definite integral, makes no difference, get that formula, don't we? Right? We'd proved this initially with Riemann sums, and then generalised it with line path integrals. Kind of similar, aren't they? Right? So it's not too much of a stretch to think, you know, there's a bit of symmetry in maths. You know, if formulas sort of make sense sometimes. So, you know, I'm an applied mathematician. I don't care about the proof unless I really need to. Right? To me, that looks nice. Right? It feels right. You know, instead of all this proofy, pure math rubbish that my colleagues would worry about. Anyway, so you sort of see the similarity. Right? Let's have a look at an example. Let's say we've got, to find the area of the surface, the part of the surface z equals x plus y squared that lies above a triangle in the xy plane with vertices 0, 0, 1, 0 and 0, 0, 0, 1, 1 and 0, 1. Right? So what I've got is I've got a triangle in the xy plane. I've got this surface sitting above. What I want to know is what is the surface area on the surface that sits directly above this triangle. Right? Now, because it's x plus y squared, cylindrical and spherical aren't going to help, brute force it. Right? Let x equal u and y equal v. Right? So my parameterization is just x is u, y is v, so z becomes u plus v squared. Right? And my region in the uv plane, which is the xy plane, because I've let x equal u and y equal v, looks like this, doesn't it, right? The triangle with 0, 0, 1, 1 and 0, 1, right? Right, so that's obvious, that bit there's the line u equals v. I've decided, just for the hell of it, to integrate with respect to u first. So u goes from 0 to v, v goes from 0. You could do it the other way around, of course. You could have v going from u to 1, and then u going, we know it makes no difference. I need to do a bit of algebra, all right? I need to find the two tangent vectors, I need to find their cross product, and then I need to find their length, right? So it's a process. All right? And remember this, the formula's on the formula sheet. You don't have to, you just have to memorise how to do it. Like with a lot of things with multiple integrals, it's just more work, all right? Turns out the length of the tangent vector is that, so I've got to integrate this. Now, here's the reason, because I could see what was going to happen. When I got to there, technically I could integrate this first with respect to v or with respect to u. Right, now, integrating that with respect to v first, inverse trig substitution, and not a nice one. Right? So integrating with respect to u initially seems easier, and fingers crossed the limits work and give you something nice to do, right? Which it does. Nice, simple substitution. Right? But of course, technically, it makes no difference. Right? There's another example I wanted to go through here that I spoke a bit about yesterday. We know the surface area of a sphere of radius a is 4 pi a squared. We all would have learned that years and years and years ago. Prove it. Right? We're given the formula, but prove it. How would we prove it? Right? Right, so basically what I want is the surface area of a sphere that sits above in the xy plane that sweeps out the whole sphere, basically. So being a sphere, spherical coordinates, right? It's got a fixed radius a, so I do x, y and z in spherical coordinates where I've let u and v act as theta and phi. You could do it in theta and phi, it makes no difference. I want the whole sphere, so I want theta or u to sweep out 0 to 2 pi, and I want v, remember the second angles from the positive z-axis down to the negative, so I want v going from 0 to pi. I need two tangent vectors, right? So I find partial ds du and partial ds dv. I find their cross product, bit messy, right? But remember, always with trigs, hopefully there will be some sine squared plus cos squareds in there. You'll notice in the k component, or the z component, you've got a sine squared u and a cos squared u with common factors. Right? So that always cleans up nicely. Right? Because the next step is you need the length of this rubbish. Right? So the square root of this squared plus this squared plus this squared, which looks awful. Right? But remember, sine squared plus cos squared is 1. Not too bad. Right? You take the positive square root. If your answer is negative, all that means is you took the wrong square root. You just ignore that minus sign rubbish. A squared sine v. So then the area is just the integral of this, where v going from 0 to 2 pi, u going from 0 to 2 pi, or the other way around. Makes no difference which order you do it in. And lo and behold, proved. Right? And that's what we can use this to find all sorts of things. Now, I want to do one more example. This is from the practical classes next week. Now, the main reason I do this one is because this one always causes trouble. So, and I like this question. Don't laugh. Right? Let's have a look. I want to have a look at this one. You don't have to write it down because you're going to get solutions for this anyway. All right? But this one shows a couple of tricks. So I'm going to reword the question a bit differently, but the solution's the same. Let's say I asked you, find the area of a triangle, seems easy so far, in the XYZ plane with vertices at 1, 1, 1, 4, 2, 1, and 1, 2, 2. Now you've probably done this sort of question before, right, when you do 3D geometry. When you first learn about these things and you learn about, you can find the distance between points. So let's visualise what's going on. Let's say that we've got one corner's at one point, that corner's at the other point, and that, right? So I've basically got a triangle that links that corner, that, and that corner, right? And I want the area of the triangle. Of course, we all know the area of a triangle is half times base times height. Now, but if I wanted to do it that way, that's a lot of work, isn't it? I need to find the lengths of the three sides. Now, I can do that with distance formulas, not too bad. All right, I could find the lengths of all three sides. I then need the length of the hypotenuse, bit of Pythagoras, then half times base times height. Yeah? Then when you learn about vectors and things like cross products and dot products and things like that, you would have probably answered a similar question with vectors. Right? You would have created two sides of the triangle as vectors, and their cross product will give you the area of a parallelogram. Everyone remember doing this sort of question? And so half the parallelogram, so you could use vectors to, one use of vectors is, let's say you've got two vectors like that, all right? 2D or 3D. Now you can find the area of a parallelogram using dot and cross products. Right, and then, because it's a parallelogram, half of it is the area of the triangle you're looking for. Right? You could do this with integrals as well. Right? And one thing I really like about when you learn more and more maths is how all these things and all these more advanced maths make life easier. Like, we don't invent all this stuff just to annoy students. Right? We do this because it makes things easier. Right, so solving it the first way, half times base times height, that's a lot of work. Doing it with vectors is actually also a little bit, it's a lot of work, probably a little bit easier than trying to do it half times base times height though. Doing this with our formal definition of surface area from an integral is the easiest. Right? This is one thing that always fascinates me about maths. As you learn more, things become easier. Right? Classic example is, remember when we were doing the half angle substitution, and I said, I mention it because it's weird, to show you some integration techniques are really weird, and you have to do things that you would not even imagine would work, but somehow magically do. And there's no magic, but you know, when you're a student you think it's magic. Right? But there's a couple of reasons. It's not talked about much, it's not in many textbooks, and the reason is because as you go on, and when you start doing calculus with complex valued functions, there is a far simpler way to do those sort of integrals with something we call contour integrals. It makes life much, much easier. Right? And that's one thing I've always been fascinated about maths. The more things you learn, the things you did in the past are easier. Although what you've learnt is much more complicated, it makes other tasks easier. And this is a good example. Right? Now, the first thing I would have to do is come up with a parameterization. So this triangle is a surface. I need a parameterization. Now, everything's all straight lines. Why don't I make life easy? So I want to come up with a parameterization. Now, I'll do it like here, so when you look at the answer, you can see what's going on. I've decided to do it just so it doesn't matter, matches with the solution. That corresponds, right, because I need to do this in terms of u and v, right? Let's say I decide that I want the point 1, 1, 1 to correspond to u equals 0, v equals 0. Remember, parameterization is not unique. Let's say that one I want to make u equals 1 and v is 0. And let's say I make that point, right? That would make life as easy as possible, wouldn't it? Right? A bit like a straight line connecting 2 points, t equals 0, t equals 1. Right? Here I need things connecting a surface connecting 3 points to make a triangle, so that's the easy way to do it. Right? You'd move the points around. I could let one of them correspond to u is 47, v is 38, but why the hell would I do that? right? Make life easy. Now, can I think of the same trick that we were doing when we connected straight lines? So if you think about it, right, taking that idea that we did with straight lines, that will do it for me. Because when u is 0 and v is 0, I'm at 1, 1, 1, aren't I? Right, because the two square bits drop out. When u equals 1 and v equals 0, the second square bracket drops out, and the 1, 1, 1's, I'm at the point 421, exactly where I want to be. And of course, when u equals 0 and v equals 1, I'm at the point 122. Right? And I could do this because they're all straight lines. Right? So if I do all the vector algebra, that is a parameterization that will work. Right? And oh, I'm sorry. Right? And I can check here. Well, when u and v is 0, I get 1, 1, 1. When u is 1, v is 0, I get 4, 2, 1. And when u equals 0, v equals 1, I get 1, 2, 2. Perfect. Right? So essentially, I've taken this. What have I done? Right, imagine, basically, what I've come up with right, this is not drawn to. Right? I've got some triangle, I haven't drawn it right, but you get the idea. I've got some triangle sitting in 3D, and I've come up with a mapping that looks like that's basically what I've done, isn't it? Right? Because I had 0, 0, 1, 0 and 0, 1. Right? So now I'm going to integrate over du dv. Right? So I'm doing a double integral, so it's fairly easy to work out that that bit is the line u plus v is 1. You need a line that goes through 1, 0 and 0, 1. Right? You know, so I could integrate, doesn't matter how I do it. Let's say I decide I'm going to integrate first with respect to, I could describe this as like so, or, of course, you know, small sweep, big sweep. Right? All right, now, what does my formula tell me? Well, my formula for doing this, calculating this area, tells me that over some region D in the UV plane of or dv du, right? That's what the formula is telling me. Right? So I need now to construct a normal vector. And so I've found that S was 1 plus 3u, 1 plus u plus v. Now at this stage you're probably thinking, there's no way this is frickin' easier. Bear with me. I need the two tangent vectors. Which are those? Make sure I haven't stuffed that up. 3, 1, 0, 0, 1, 1. I need their cross product. Right. We remember how we do this. We come up with a fictitious matrix. The easiest way is to that I find is to copy out the first two columns. All right, so the x components 0 times 0 minus 0 times 0, 0 minus... Please don't do it as fast as for me. I'm going to cheat. All right, I've stuffed something up. What have I stuffed up? I times 1 times 1 minus I times 0. Right? I need its length. So this is the normal vector. I need its length. That's easy to integrate. All right? So now I can find the area. All right, I'm going to do, doesn't make any difference. All right? Done. Right. Again, this is you could do this several different ways, right? But doing volumes and learning about how to do volumes, lengths, and areas with integrals lets you handle all sorts of shapes, right? And almost all of the area, surface area, volume formulas you're used to for cones and sphere, and all these shapes. This is how we prove every single one of them. As long as you can do the integral. And if the shape's simple, you'll always be able to do the integral. The thing I like about this one, as I said, we've already learned, so you would have already learned several ways to solve this question, right? But this way is actually the easiest. Believe it or not, it's much easier, right? Because doing it the old way with half times base times height, that's a lot of algebra. Yes, it's just numbers, but it's a lot of algebra, a lot of work. You need to find the lengths of the three sides. Then you need to pick which one is going to be your base. You have to find the hypotenuse, unless it's lucky and you get a right angle triangle, which never frickin' happens, right? Do it that way. You could do it with vectors. That involves cross products. So did this one. But this cross product is easier than the vector way because it's all constants, right? And then yes, you've got a double integral, but it's all constants, right? But the main thing to take away from this one is this idea of doing the simple parameterization. The way we parameterize straight lines, we think of it as endpoint plus start point minus endpoint. Start point plus endpoint minus start point times t. And that works because when t equals 0, I'm at the beginning. When t equals 1, I'm at the end. And you can keep going in higher and higher dimensions. So this is the logical 3D extension of that, right? And this works because things cancel. You can see the way I've written it straight away. When u and v is 0, I'm at 1 point. Right? So you can use this idea for all sorts of things. So the only time I would get you to come up with a parameterization for surfaces is either cylindrical, spherical, brute force, or straight planes. Now, if it was a question like this, I'd give you a hint, right, and tell you this is what to do. So, but we can construct very simple ones by taking this idea that we were doing for straight lines. Okay? All right, so that means we are basically done, finally, with integrals. Right? The last topic we're going to cover is something called differential equations, which involves integration, but we're back to definite integrals. Indefinite integrals. I don't want to start that now. I'll wait until the last lecture for that one. All right? Now this isn't a typical example, this is just showing you the uses. Please do work through this one in the lecture notes and make sure you understand the steps, and of course remember the formulas given to you on the formula sheet. Okay? But we'll leave it there for today. We're on the home stretch, one more topic to go. Okay? I'll see everyone on Thursday.